So today we have a hard problem. We're given some batteries and each represents some number like 1, 2, 3, and we given the number n. It's how many computers we have, and we asked to find how much time it is possible to run n computers together simultaneously. So let's look at this example, for example, and we can run this two computers like this. 1 minute, it decreases by 1. Then we have to take this one and ignore this one, and finally we can take this one and this one, and it becomes zeros. So it is like 1 minute, 2 minutes, and 3 minutes. So this is how you can imagine how it works, but the actual algorithm is pretty tricky to code, because intuitively you can take the largest, okay, you take the largest, and you go minute by minute, but imagine you have like these numbers, like 1 and then 10 to the power of 5, like this. You can't go minute by minute in this way, so you have to do it like linearly. And let's observe some properties about the solution. So we ask to find time, total time, that we can run. So imagine if the total time is 0, can we run it at 0 times? Of course. Imagine it is just 1 minute. Can you run for 1 minute? In this case, you have to look at how many batteries you have. Like 1, 2, 3, you have 3 batteries, and how many computers you have? Like 2. If you have, for example, 4 computers and only 3 batteries, you can't. But if you have 2, you can. So it is also true. And now let's imagine it is 50 minutes. Can you run for 50 minutes? No, because the maximum battery capacity is only 3. So you quickly can answer it is false. So in this case, you have like true, true, true when time goes, and eventually you have false, 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 and so on. Some value of time where the true comes to false, and this would be a maximum, and this is actually our answer. So you can do it's kind of sorted order, like you have true and then you have false, and the time grows linearly, so you can use binary search, like minimum, maximum, time, maybe 0. This can be any value, like total sum or just long max, and then you have to do binary search. You have to take minimum, and this is your given time. And the problems became about can you answer the question, can you run at a given time uh, and notebooks? You have given more data like t given and n also given, and you have batteries. So it's much more richer kind of information. And let's look at what else we are given. Okay, the T can be tested. It's like, for example, can it run in 3 minutes to computers? We previously calculated yes it can, but how can we answer for particular T? What is the algorithm? Let's look at what else we know about this. So we have two computers and we have given time 3. The total number of, like I would say, energy is 2 computers by 3 minutes. It is 6. So this is kind of hints us how we can have some maximum value. Imagine we have t equal like 30. This would be a 2 by 30. It is 60. And it is much more than the total sum of these batteries. And this hints us to another kind of value we have to look at, the sum. Sum is 2 plus 2, 1 plus 2 plus 3. It is 6 for this case. But there are some corner cases where we can't just use this sum. For example, imagine we have these batteries like 1, 40 and 40 and equals 2, but the sum is 81. Okay, in this case we can actually use at least at most 40 minutes of 2. But if we have like this 1 and 40 n equals 2, can we use 41? No, because as soon as we used first minute, we have 0 for the second notebook, and that means we can't run any longer than 1 minute. So that gives us a hint about what kind of sum we have to compare our energy. The energy is T times N, and sum is how much you can take each battery at most. So, for example, you have to test T equals 39, and in this case, from 1 you can only take 1, and from 40 you can only take 39, I would say, and together it is 40. Yes. Okay. It is T and the N is 2. And 2, this is our sum we can take from this battery theoretically. And the total energy we want is 2 by 39. It is like 70, I don't know, 78, of course, yes. And we compare this 78 with 40 and see that our 40 is much less, so we have not enough energy we can take from each battery. So this is our entire algorithm we can answer, can run this question, and the rest is just mechanical work about the money research. You have low, high, middle, and you can you testing every middle, and if it's okay, you updating the result. Result is should be maximum, and you updating the successful branch of the if. And can run is total energy, and you compare this total energy with how much you can take from each battery. And you can take only T or the entire battery. Minimum of that. Battery is 1, you should take 1, even if your T is like 39. And if your T is 1 and the battery is 40, you should take T1. And then you compare if the total energy is less or equal to the sum of what we can take from the batteries. I use this kind of sum for the highest value, but it is not necessary because the binary search is still logarithm, and for the long it is 40. It is 64, I think. Yes. So it is not necessary optimization. So I almost solved like myself, but the hardest part is to eventually answer this question. And even I have in my mind that I can use the total, like have total 7 time 3 computers, and the total energy is 22. I have a hard time to comprehend how much you can take from each battery. It's kind of not very easy to think of it yourself. You either took the entire battery or the T. For example, if T equals 4, you can take 2, 2, and 4. And that would be 6. And the total energy is like T times 2 is 8. So you can't take 4. And let's look at the test case for this. 2 to 10. Do I have it? Yes. And you have test result. It is 4. So let's look at it. It's interesting. So we have 2 batteries, and this is the capacity. And imagine we have we're testing the time 4. Can we run 2 computers 4 minutes? The total energy is T times n, it is 8. And then we iterated and computed how many energy each battery can gives us. So it can give at least at most its capacity, or T. So we have 2, 2. So it was my arithmetic mistake. So because this is not 6, it's 8. If I didn't make this simple arithmetic mistake, I would eventually immediately spot this kind of trick. But I did this kind of arithmetics, and it was preventing me from understanding. So this was actually a solution, but I missed it. So I have to look at the hint. And the hint was about the same intuition that I already have. So I look at the description and I found this one. It pretty much answers this question, how you can test the time you can run. And this is like each battery can contribute at most T energy units, or its capacity, and you can just sum it up. So it's an interesting question why you can sum it up like this. Why you're not doing like parallelization? Why it's eventually like evens out with the actual answer? So I don't know how to answer this question, and it's actually very hard to explain. It's also theoretical and hand wavy, and I don't have a precise intuition about it. So we have like why you can do this sum and uh, not looking for corner cases. Yes, we compare this to the total parallel, but why we can do this sum? Why it's allowed to do this kind of blind like single sum operation? I think this is a more honest solution. So it is average charge per computer. So does it compare it to it? No, he's doing like this. It's the same. It didn't compute average. So it is kind of hard to understand on the fly. I will try to do it. So now you can watch how I solved it in 34 minutes.